have disqualify factors, and then there would have been a corresponding U-channel diagram. So this fact that this numerator identity is there is actually inherited from that joint. So maybe I should have used a different representation from the start. But this is just a very simple example that if you actually look, especially when you look at when you have many external fermions, you can actually land on numerator expressions which are already gauge invariant from the very beginning. And therefore, if color kinemax duality works, it has to work on these numerators because you don't have any freedom. But you can easily convince yourself that these diagrams have to be gauge invariant. Because, for example, if I dress up the lines with an additional flavor index, then this has a different flavor structure than this. So definitely this have to be different. This have to be independently gauge invariant. Okay, so let me say a little bit more. Okay, so what do you do with these diagrams? Well, so the point is that once you have the numerators satisfy color kinematic duality, then you can construct gravity amplitudes. So in this case, what kind of gravity amplitudes can you construct? Well, let us start by just taking this diagram and replacing, maybe I should do it over here. So now let me convert this into a gravitational amplitude. So what I should do is that I should remove the color factor, and I should just, let's say first that we take the same numerator twice, so we just square it. So this is an amplitude. And what's the amplitude for this? This is an amplitude between photons. So in particular it's minus elicited photon, it's less elicited photons. But you notice that this only has one channel, so in fact it's between two different types of photons. So this is a 3 minus and it's gamma prime, so it's a different photon. And it's 4 plus, and it's a different photon here. Now if you add this diagram plus the other diagram, then you get both channels that you would expect. So indeed you will get, if we do it down below, then you will get an amplitude just for a single Q1 photon. So if I add this term and that term, so let me denote it like that, then I can just remove the prime here. Then it's just 4 photon amplitude. It's basically it's 4 photons which only interact gravitationally. Now I could have done a different thing. Instead of squaring each numerator, I could have taken the complex conjugate. So let me do that over here. So I can take, so this is the first numerator, and then I take the second numerator to be the complex conjugate, and the complex conjugate is just changing the brackets. And then over S. Now because of this identity that I have here, this kind of factor assembles into a Mandelstam invariant. So in particular, this factor will be U, but this factor will also be U. So this is actually U squared over S. And similarly, the other factor We'll also look at integral. Let's write that. So this will also be u over t. So, well, maybe you can guess what sort of amplitude it is just from the structure. This is a scalar amplitude because it only has quantities which has no helicity, no little group weights. So if I add these two together, I basically get an amplitude for scalars and they're complex scalars, so in particular it's going to be, this is going to be complex conjugates. So the whole amplitude is this, 1 over s, is 1 over t. And in particular, what you wonder, what kind of scalars are they? Well, if you embed it in another, if you think of the spectrum of supergravity theory, this is just a linear combination of the dilaton and the axion scaling. Okay. Now you can continue and do this for more complicated cases. You can continue and do it for 5 point. And I don't know if I'm going to work that out, but maybe I can just sketch it. So So 5 point. And let's consider the case that we have 4 fundamental particles, and then we have 1 gluon. We have some diagram like this. 1, 2, 3, 4. Well, do it the other way around. 4, 5. So this is going to be gluon, and the other ones are going to be quarks. So there's going to be this diagram. So now let me just schematically denote the C1 N1 over D1. And there's going to be, don't worry, I'm not going to draw all the diagrams. There's 3 of them. So it's going to be this diagram. Let me not put labels because it's not so interesting. But I'm going to call it C2 N2 over D2. And lastly, there's going to be a slightly different type of diagram. It's going to look like this. So this is going to have 3 gluon interaction. This is going to be, let me call it just C3. And 3 over D3. So these 3 diagrams, they're going to satisfy a correlation. So it's going to be that N1 plus, there's a minus sign, but sign doesn't matter so much, minus N2 is equal to minus N5. Of course, the overall signs depend on exactly how you draw the diagrams. But it's going to be this identity. And in total, that's going to be 15 diagrams. So this is only 3 of the diagrams. Sorry, I take it back. That's 10 diagrams. So this is just a subset of those diagrams. And for each, and there's going to be a triplet of diagrams, which looks the same way as here. It's just going to be different permutation of the external legs. So there's going to be a number of these identities, and all of them are actually going to be automatic. Just when I find my diagram, all of these identities are automatic. And the reason why they're automatic is because the interactions are simple enough. There's not a single diagram which has a 4 gluon vertex. the most complicated interaction is the 3-gluon vertex, and therefore actually color kinematics reality is automatic when the Feynman rules. But now, I mean, you can go home and write out what these are. They're not so complicated. And then, once you have them, you can construct the corresponding gravity amplitudes. So, you can start off by doing the photon amplitude. So, 4 photons. And they're going to be, in this case, it's going to be alternating helicity. And then you're going to have 1 graviton. Could be denoted like this. And in particular, in this case, I picked the particular helicity for the graviton. And this is going to be a sum over these 10 diagrams, as I said. So this is just going to be Ni squared over di from 1 to 10. But all the diagrams contribute. And another thing you can do is to write down the scalars, as I did before. So and they're going to be complex scalars, so I'll put a bar, and then let's say we put the same helicity for the gravitons. So this is going to look very similar. Except we're going to multiply n by n bar, which is just a complex conjugate. So one thing to note is that because ni satisfy all these Jacobi relations, the complex conjugate also satisfies the same Jacobi relations. But if you take the complex conjugate, that's going to cancel out the phase weight that the quarks had. So that's going to give you scalars. Okay, so here's a very non-trivial example. We're using the fact that just the simple Feynman rules in this particular case satisfy color kinematics duality. It's very simple to just construct these rather complicated interactions between matter and gravity. Now, this is some very explicit examples that I showed you, but I haven't convinced you that in the literature there's much more complicated examples of loop calculations where this all work. So let me just list a few examples. So in particular, been a number of calculations, and let's just mention a few of them. So there's been 3 and 4 loop calculations in N=8 supergravity. There's been 3 and 4 loop calculations in N=4 superdiagonals. Sorry, supergravity. And these calculations were done in order to figure out the ultraviolet behavior of this series. And that's still a currently ongoing investigation, but it's not the topic of this talk. Then there's been some calculations at 1 and 2 loops. So obviously this has gone very far because there's a lot of symmetry, and amplitudes are much simpler. But once you start talking about lower supersymmetry, it's a bit more complicated. So this is still fairly high. So this is 1 and 2 loop calculations for between 4 and 8. So all of these amplitudes have been calculated. This is at the 4 point. All of these are actually 4 point amplitudes. I should have said that. Well, except for this has also been done at 5 points. There's been, let me just mention the other one. So there's been 1 loop calculation in self-dual gravity, dual multiplicity. There's There's one loop calculations in, let me say this, so one loop in n less than 4 supergravity plus matter, where the matter has the same amount of supersymmetry. And this has been done both for abelian and non-abelian. So there's a lot of evidence that it works for fairly non-trivial calculations. Any questions so far? Yeah.
In game theory, color factors could play some role in anomalies, for example. Do those kinematical factors also have the same similarities?
Yeah, so that's a topic under current investigation, and there's some very interesting details there. So there's a very interesting interplay between the color factors and the numerators, and also furthermore how the gauge theory anomalies is related to the gravity anomalies. But yeah, I don't think I can say any specific details because there's nothing published in the literature yet, so I think you just have to wait for the results. Was there another question? Yeah.
In your previous example with the 4 quarks, you mentioned that when the numerator satisfies the relation inherited from the adjoint representation, while the color factors didn't satisfy the relation because they were in the fundamental. I was thinking that could the numerator satisfy the relations inherited from other representations?
Yeah, that's a good question. I think that's possible. Although I mean, it has to be the least constraining representation, though, because this numerator is supposed to be valid. No, I think you're right. Yeah, I mean, there's certainly special relations which are only there for fundamentals. Yeah, so you can turn it around. So if there's a relation just for the fundamentals, then they carry on actually to that joint as well. So it's a both-way communication actually. Yeah, that's a very good point. Yeah.
Both Yang-Mills theory and Einstein theory have infrared singularities, and the singularity can also be handled in this scheme.
Yes, there's been some work analyzing the infrared singularities, mainly by Chris Waite and collaborators. It's not so obvious how the infrared singularities are related diagram by diagram, though, but it's a much more tricky, I mean, it's actually easier to analyze ultraviolet behavior diagram by diagram, whereas infrared behavior is a bit trickier. But there is papers in the literature, we looked at it, and in particular, what they looked at is that because gravity has a milder infrared behavior, they were looking at whether you can use this relation to actually constrain QCD infrared behavior. But they found that the constraint that gravity sort of feeds back are precisely stuff which are already known, so it's all consistent. So there's no further constraint. Okay, any other questions?
One more.
Yeah.
What about ultraviolet behavior? Scattering amplitude at high, large S?
Yeah. Large S. This is not something we looked at Now we always consider small or soft or not hard external particles, and then we look just at the ultraviolet divergences in the loop expansion. We never looked at when we actually have hard external particles. I mean, the amplitudes of, well, that's not right. Sorry. There is indeed a paper on that. In fact, there's more than one paper on that. So there's some analogous relations in the Reggie behavior, which is noticed by Lipatov and collaborators. In particular, it's exactly this process. But if you add up all these diagrams, and then in the hard limit, where these legs are hard, exactly like drawn, then what happens is that the registration, or the answer that you get for gravity in QCD are related exactly. There's an effective vertex, which is exactly the square of the QCD vertex. However, there's an additional contribution which doesn't come from the QCD, so it's a bit more complicated actually, which is a bit surprising. But I think it might be because it hasn't been studied in further detail, so that's just an initial investigation. Okay. I'm unsure, I only have 5 minutes left, so I think I should not start on my next topic. So the next topic would have been how to construct this Einstein and Mills theory, but that's something I hope to start talking about next time on Wednesday. So I think I will probably stop here.
Other questions? Okay, so his second lecture is on Wednesday.
Yeah.
Just have a quick one announcement. So we still have about 5 places left on the dinner tonight, and for those of you who are interested in joining, because we will be in the booth of 40 people, so it'll be just us. So I think it will be a very good opportunity to talk to other participants. So if you are interested in joining, then please let Jesse outside know and just pay the price, $500. Okay, so thank you.